Hello and welcome back to Calculus 2, section 9.4, working with Taylor series. So, we know how to approximate functions with the series, and we know that this series are represented by polynomials. We also know that it's extremely easy to differentiate and integrate polynomials. We also know that there are certain functions that cannot be integrated at all. And some functions are incredibly difficult to integrate, and then you have whatever you learned in Calc 2, which is by the community considered easy to integrate, even though you might argue differently. So what I'm going to do is I'm going to consider sine of 3x. And let's say that I want to integrate that. Well, we all know the formula for it. The integral of sine is negative cosine 3x. We have to divide by 3. We put plus c and we walk away. No coffee. But now, is there a way to do this differently? And the answer is yes. We can expand sine 3x using power series, Taylor, right? Polynomial. And then instead of integrating the sine 3x, we integrate 3 or 4 terms of that polynomial. So what do I know? I know that sine x expands as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And since I'm working only 3 terms, I'm going to stop there. But I could have gone and said negative 7 over 7 factorial and so on. But they're not asking me for sine of x. They're asking me for sine of 3x, which is where that thing on the composition that we had in 9.2 in the properties kicks in, which allows you to replace each x with 3x. So now it's going to be 3x instead of each x. It's a very simple thing to do. And now you expand that into a polynomial. Now again, is it overkill for this problem? Sure it is. For the next problem, not so much. You'll see that. So what is the sine 3x? Sine 3x is expanded as 3x minus 27x cubed over 2 times 3, and then that cancels into a 9, plus 3 to the 5, so that's going to be 3 times 81, x to the 5, over 2 times 3 times 4 times 5, if you were wondering why I'm picking certain values. So this is 3x minus 9/2 x cubed plus 3 and 3 cancels, and I have 81 over 60 x to the 5. They should say approximate, not equal. Use algebra. So that's what we have. And now you can integrate this. And the next problem is very interesting. Integral of e to the x squared dx. Can we use U sub? Hell no. Can we use anything else? And the answer is no, you cannot. You cannot use anything else because we don't have those methods to solve this in Calc 2. So what should you do? Well, what I know is that e to the x is given as 1 plus x squared over 2 plus x cubed over 6. Not equal, approximated, because I'm using 4 terms. Now, I say composition, where I am replacing each x with x squared. So that gives me 1 plus x squared instead of x, plus so you see the structure, and I'm replacing every x with x squared. And now it's time for algebra. So e to the x squared is approximated by 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6. So can I compute now, let's say x is equal to 5. Can I compute this using the polynomial? Why not? Yes, because it's far from 0. Observe that I used the Maclaurin. I expanded E. Now I can use whatever the hell I want because the problem didn't specify to me what to use. So, in this case, instead of integrating e to the x squared dx, we are going to integrate 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6 dx, and be happy. However, if you have the integral from 5 to 5.2 of e to the x squared dx, how's this different than the previous case? Now we have a. And what's a? 5. Common sense. 5. So now, everything we did in the previous problem doesn't fly anymore, right? Because your expansion now has to have x minus a. So, your e... Did I start a stream? I thought I did. Oh yeah, I did. All right. It didn't update the website. Good. So, so now I have to expand and I have to shift. So now your e to the x is going to be 1 plus x minus 5 plus x minus 5 squared over 2 plus x minus 5 cubed over 6. Not equal, but approximated. We have to expand around 5 because we have a definite integral that works in the neighborhood of 5. So, what we have here is now much more work than what it used to be because you have to expand all of those, add them into polynomials, and then deal with that. Well, we're not done there, right? Because we still have our x squared that needs to peek in. So there it is. And this is where each of the x's becomes x squared. So the question is, how annoying this gets to be, right? So you want to see Maclaurin series because you don't have to deal with x minus 5 squared, x minus 5 cubed. And then especially when you have this type of thing where you have to replace each x with x squared or something, then it becomes worse. This is 1 plus x squared minus, oh, I could have combined those, plus 1/2 of x to the 4th minus 10x squared plus 25 plus 1/6 of x to the 6th minus 15x to the something. So that will be 4th plus 15x squared minus 125. There we go. Distribute the half, distribute 1/6, add like terms, and you have your polynomial, sixth order polynomial to expand this. But then you'll be integrating polynomial and you plug in 5 and 5.2, and there you have it. Do you see a major limitation of what we are doing right now? Anyone?
Does that mean if you have anything like, say for instance, you're integrating 0 to 5.2, would you center it at 0 and then...
No, it's useless at that point.
Well, I'm saying because then it gets so off because it's such a far distance.
So if you are to center it at 0 there, we're talking 20 terms, man.
Yeah.
Right? It's gonna be awesome. I'll cry. Use Mathematica. Use Mathematica. That's what we do. This used to be cool when being do what?
The x squared. Why do you put the square there? The way.
What do I do? What?
The bottom. You scroll down. Right there, e to the x squared.
That's the problem that I need. So I have e to the x, and I memorize the expansion from that. I know that from the chart. But that's not what I need. I need to replace x with x squared, and that replaces each x in expansion with x squared, and that triggers algebra. So working with power series, Taylor's, right, is you have a function that you know, and you transform that function. And when you transform that function, you integrate polynomial in that case, which is easy. Okay. Now, those of you who are more vicious, you guys will probably memorize a lot of these power series.
The one that 25 are wrong, right?
Are you referring to like the Taylor expansion?
Yeah.
Or the most important ones to know would be like your e to the x, sine x, and cosine x? Or should we get more messages going?
Well, if you look at the textbook, this is the page 694. So page 694 gives you the Taylor expansions for those functions that we see most of the time in sciences and engineering. However, Mathematica just plows through this, so. But if you observe, to get that nice 1 plus x squared plus x cubed plus x to the 4th, that came from 1 over 1 minus x. And then if you change the sign, it keeps the same thing except just alternates the sign. See how nice they work out? So 1 over 1 minus x gives you the 1, then it's 1 plus x plus, right? And then when you change the sign, it starts alternating signs. Now you have a sine and cosine pair where the sine is all odd exponents and the cosine is all even exponents. This is x to the 0, right? 1. So you have 0, 2, 4, 6, 8, and over here 1, 3, 5, 7, 9, and so on. Now look at the hyperbolics. You can't see the hyperbolics, but I will scroll so you can see hyperbolics. If you look at the hyperbolics and sine and cosine, they're the same except sines and cosines. Hyperbolics don't have alternation in signs. See, that one and that one are the same except this is plus, 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 and this is plus, minus, plus, minus, plus, minus. Same goes for cosine. It's extremely easy to memorize all of these, actually. When I took Calc2 15 years ago, I knew all of them, but I didn't know what to do with them. So it was terrible. And there's your e to the x, which is what we used in this example. So yeah, fun stuff. I already showed you that when you differentiate sine, you get cosine. Derivative of x is 1. Derivative of x cubed is 3x squared. And then that 3 and 3 factorial cancels into 2 factorial. 5 drops, x to the 4. And then 5 cancels the 5, leaves in 4 factorial. Yeah? Now consider the backwards. What's the derivative of cosine? Negative sign. Does it work?
No.
Hell yeah. Derivative of 1 is 0. Derivative of this guy is x 2x over 2, which is just x. But it's negative x. And this is x. So you see that all the signs will be opposite. You pull out the negative, you get all the right signs. So it's minus, and then the sign, so the derivative works.
Well, you practically have to know it's 1.
What happened?
You practically have to know it's 1.
It's really powerful. So, you know, when we tell you in Calc 1, the derivative of sine is cosine, you go, why? Yeah, go do this long, exploitation procedure with limit. Or you do this. Now, this is cheating. If you do the proof by this, it's cheating. Because you're using derivatives, right? You're trying to prove that the derivative of sine is cosine, but each one of these coefficients over here is obtained the derivative. It's kind of cheating. But it's really neat that it works that way. It has to work this way. It's mathematical. It has to work. So yeah, power series. Awesome stuff. Awesome stuff. I love it. And that ends chapter 9. Exam is next week. Your quizzes start tomorrow at 6 a.m. You will have another SI session. My office hours are there, tutoring center is there. So I'll see you Tuesday. Well, yeah, it's lab time. So I'll see you Tuesday.